Hello everyone and welcome to Module 6 in classification. Jumping right in. Um, Module 6 deals with comparison of various sort of models and ways that you can consider which one is doing better. So basically the details here in this model, we're going to talk about things like comparing various classification and analytical models. So how do you compare them? Evaluate the model comparison problem, employ the test of significance, statistical significance to the model, so you'll potentially want to know that sometimes statistics comes to play here. Compare two classification models using a receiver operating characteristic ROC curve tool, so specifically the area under that curve is what's interesting. And then measure the training time, robustness, interpretability, and scalability of each model. So jumping straight into it, what is classification comparison or model comparison? And it's basically figuring out what model is doing best in your particular situation of classification. And the reason being, you may want to use obviously the best one. And sometimes you deal with this concept of hyperparameter or parameter tuning. And the idea is that you need to know what is better, A or B. And sometimes the difference may be subtle, and there's various other characteristics to consider when we talk about models as well. So why do it? Well, you typically don't want the worst model. So the idea here is to find the best classification. You also need to know what best means, right? So that's kind of the first thing, is figuring out what best means, and the best sort of outcome can be achieved, and it can be a complex problem because there may be several factors coming to play. It also is a common, the common approaches that you use during this sort of thing includes things like dealing with calculations of accuracy, recall, confusion matrices, area under the curve, as we talked previously a little bit, statistical methods. You may be doing a t-test or something to determine if it really is better, and sometimes you want to have some sort of an evaluation framework in place to help you figure it out. So when we talk about comparing metrics, you need to first of all decide what good looks like. So in some situations, for example, a false positive, it could be very bad. Other situations, a false negative might be very bad. So knowing which one is the worst outcome, because if you're dealing with something like maybe testing for a disease or predicting a disease, you probably would figure out which one of those is the worst. So if you have two different models, obviously you would like the best of both, right? You would want them to not have either false positives or false negatives. But if they do, which is worse? And being able to pick between the two. Sometimes we'll have some sort of a formula that we use that's based upon some weighting. Maybe you do something like area under the curve is the primary thing, and then you may consider some other factors into it as well, like execution time. That's something to consider. It's not just about the number of say accuracy. It's also how long does something take to figure out an answer, what sort of resources are involved in figuring out that answer, and so on, so that it may be a much more complicated answer than just simply picking the one with the lowest score or the highest score, which is whoever it is you're trying to do. The receiver operating characteristics, your ROC, and the area under the curve, AUC, are one of the most commonly used metrics you're going to see. The combination of those two things together, it is a very common way of measuring the effectiveness or the viability of a model, or comparing two things together. The basic concept here is also the foundation of something that I've talked a little bit about, which is around automated machine learning, or AutoML. AutoML basically takes this kind of concept and it utilizes a function that you define as the person who's working within an environment of what is the thing that is the measure of goodness. So if it's area under the curve, then that's what you tell it to maximize, so that you get the best outcome. So those are the kind of the high level concepts around an algorithm and a model whenever you're doing evaluations of it. There's also this concept of other factors outside of just numbers, and it's about trust. When you talk about trusting a model, this is kind of an important characteristic, and this is one of the challenges things like connectionist approaches. So neural networks faces challenges because they're very hard to explain. We don't necessarily know sometimes exactly why it is doing what it's doing. And also, sometimes it's not terribly clear as to what it is it's doing. And this is all underneath that umbrella over here of transparency. You need to be able to tell how the thing is making the choices or making the decisions that it's making or recommendations. And it needs to do so, obviously, in a consistent way. So if it's like pretty good, maybe 80% of the time, but it's really horrible that other 10%, that may not be acceptable. Oftentimes we want very little variance in our error, so to speak. We would like it to be consistently the same level of goodness most of the time. You don't want these degenerate cases that come along that really make it do a bad job. Or if you do, you need some way of hopefully identifying them, but sometimes that's not very likely. There's also this accountability thing. We need to typically make sure that we're doing things like having proper security in place around our machine learning, making sure that they are reliable, that they're robust, safe, and certain. And then fairness. This is one of the areas that is definitely an emerging field of discussion around both artificial intelligence and machine learning, which is around making sure that the models that we're training are being trained in a fair and equitable way, so that people that are being served by those models or being judged by them, if that's the case, is done so in a fair and equitable way. And you don't want it to be where they are essentially biased or prejudiced based upon maybe the data they were trained on. So you definitely want inclusion and you want diversity. Sometimes we achieve that by not keeping track of something. So not including something in your model may be one means of reaching a more equitable situation. So perhaps you don't want race or ethnicity to be included in your model because it could bias the outcomes. So these are all kind of elements of trusting a model, and it comes into this whole fair, accountable, and transparent sort of paradigm. So a very good thing to think about. It's not just about numbers, though numbers do figure into it. It's about making sure that whatever the implementation you're utilizing, that it follows kind of that pattern. Other factors that you may want to consider too whenever you're evaluating, you've got model A and you've got model B, is things like speed of execution. If it's really, really accurate, but it takes longer than the usefulness of the decision-making process, then it's not all that meaningful, right? So it needs to be fast enough to be used in the time frame that you need to know it. So if you've got an assembly line and you're determining if something that's rolling along is an anomaly or a defect essentially, then you need to be able to make that determination in the time before it reaches the basically the switching point to send it to the special place. So there's definitely a speed of execution to consider about in all of these things. Same thing if you've got a car that's looking for some sort of anomaly detection or doing some sort of classification of if a sign is a stop sign or not. You need it to make that determination very quickly so that you can stop in time. We also want them to be very consistent and generalizable, generally speaking. You want it to do well even if it sees something it's never saw before. That's kind of the basic idea. That's part of why we do the approach we're going to talk about in a moment around holding out data so that we're not overtraining it and training a model to only do well in what it's seen. So we want a high degree of generalizability and to be able to handle it. And also that ties into robustness. We want it to handle it in noisy conditions as well. So if you're doing something that classifies images, but it only works if they're really, really good images, maybe not all that useful, especially if the source of your images is not the same thing. Maybe they're really bad images. So you may actually need to train it somewhat on some noisy images. You also want the ability to be scalable, and the scalable not so much in the sense of the number of things being classified at a given point in time, although that might be important too. This is more about making sure that if it takes quite a bit of data to make a determination, that you can handle that amount of data in an effective and efficient way. And as I just kind of mentioned a little bit before, you need to be able to understand why the model's doing what it's doing. So it needs to be interpretable so that the output is easy to understand why it did what it did with a high degree of transparency. A common pattern you'll see in machine learning in general, and you've probably seen this before, potentially in a data science languages class or something, is this concept of doing basically, you take an original data set, especially one that's labeled. This is typically around supervised classification or learning. And you take it and you split it by some factor. Sometimes it's like 20/80. Kind of depends on how much data you're talking about. It could be 50/50, but you've split it by some sort of a percentage, and you take part of that and hold it out as your test set. And the idea of the test set is that we'll never see it or use it in any way during the training part, only during the part where you're actually doing the final performance estimation. So this is held out. You don't ever let the model see it. Only time it sees it is when it makes a prediction. Then you take your training set and potentially split it again into two different sets, one for validation, one for training. The idea of training is that you take that and that's what you actually do to adjust essentially fit the data with the model. And then the way that you use the validation set is to determine which one of the models is the better sort of approach. So you figure out based upon those two things which one is maybe hyperparameter tuning, maybe it is actually literally changing out which model you're using. And once you get a predictive model, then you apply your test set and figure out how well you did. You don't ever include it beforehand because you're potentially going to bias your results. And this is a very common pattern. There's other patterns as well, but that's one to definitely be familiar with. Moving over to deliverable 6. So this one's kind of interesting because it's around using a set of classifiers to use some assessment of radar pingbacks, right? So the basic idea is that you've got a set of values that you're going to be doing some classification on, and then you're going to submit a report of your findings. And this is basically going to be using some clustering here going on. So some interesting stuff. So the basic idea here is that radars basically send out a radio wave in a certain way and listen for bounce back, right? So they essentially transmit. It's an active sensing approach. They send a pulse out, and then they're listening for the return over intervals so they can determine when something comes back, where it's at, and so on. A pattern of good returns can be differentiated from a pattern of bad returns. So good returns are those that showing evidence of some structure in the ionosphere. So maybe an airplane. Bad returns are those that do not. These signals pass through the ionosphere. The received signals were processed using an autocorrectional function whose arguments are the time of a pulse and the pulse numbers. So your instruction, there are 17 pulse numbers of the instances of which in this data set they are described by 2 attributes and have 34 attributes that are continuous, and our targets are either good or bad. So what you're going to do is load in any required libraries that you need. You're going to read the CSV probably into pandas, and you're going to use scikit-learn to process it. You're going to explore the data, print out some of the part of the data set, split the data set into training and test sets, similar to what I talked about. Build a pipeline of the following classifiers. So you're going to do scikit-learn pipelines. That's an important piece of information. And you're going to do, in particular, K-neighbor classifier, decision tree, bagging, and a boost, so ensemble over here as well. And if for each one of these you basically want to train it, perform some prediction using it, and then compute the score and confusion matrix and the area under the curve, basically. So the AUC of the ROC. Then use the CN2 unordered learner method that's part of the Orange libraries to build a learning object and use it to build a classifier. Use that classifier to predict 75 data instances, compute the same sort of values here, and compare them with the ones you get up here. And then perform clustering using k-means, so also take it and do some clustering, varying the number of clusters and the number of iterations for each of the performance metrics adjusted rand index, homogeneity, and v-measure. So pretty detailed instructions. What do you turn in? So a report that's going to talk about each one of those algorithms used to perform the computation. So a brief description of what each one of those algorithms does, the results of the data exploration. For the supervised learning ones, a table containing the performance metrics for each of the classifiers comprised of the score, the area under the ROC curve, and an explanation of how these metrics affect the results. Also a comparison of the confusion matrix for each classifier. For unsupervised learning, a table containing the adjusted RAND index, the homogeneity, and v-measure versus the number of clusters and the number of iterations. So this is kind of telling you rows and columns. You can kind of piece that together. A comparison of the training time of each algorithm, and then the PySource of the code that you write. So basically your .py file. Or it's perfectly fine to turn in a Jupyter Notebook as well, if you're so inclined. So some details about the data. It's always interesting to kind of go back in time and see where this stuff came from. So it was up in Goose. It's up in Goose Bay. The system consists of a phased array of 13 high-frequency antennas with a total transmitting power of roughly 6.4 kilowatts. There's a paper that talks about this if you're really wanting to go read about it. Good radar shows are those showing evidence of some type of structure in the atmosphere. The bad don't. The signals passing through the atmosphere. Received signals were processed using an autocorrectional function whose arguments are the time of the pulse and the pulse number. Were 17 pulses in Goose Bay, and each one of them is described with 2 attributes. So that's where you get the 34 plus the 35th item, which is if it's good or it's bad. And this is, just to be stating the obvious, a binary classification task. So here's what the data looks like. Again, this is those 34 features, and with a label out at the end of good or bad. And if you're real interested, there's the data set if you want to go take a look at it and learn about it. So moving over to deliverables 7. This is kind of the piece where you pull it all together. So you develop an analytics model using the nearest neighbors classification, clustering, a decision tree, some rule-based classification, bagging and boosting, so your ensemble methods, and you compare the various analytic models. You do this by going through the Titanic data set. And as you probably know, it went down likely because it hit an iceberg, although there's some discussion around that lately. The part of that was interesting was claimed to be unsinkable and so on and so on. 1502 out of 24 passengers and crew members died. So this is kind of a morbid sort of thing, but it is an interesting and a fairly common problem to try to predict. So studies show that some groups of people were more likely to survive than others, such as women and children and upper-class passengers. Women and children, you can kind of understand. Upper-class passengers probably speaks to social inequality. You're a data scientist at the Atlantic Ocean Disaster Investigation. It's a company whose purpose is to investigate and analyze past disasters that occurred in the Atlantic. You've been asked to solve the problem regarding the Titanic disaster. You're given a training set of samples listing passengers who have survived and did not the Titanic. You're to build a model and given a test data set that does not contain survival information that can predict whether a passenger would survive or not. This is because this data set's coming from Kaggle, and the Kaggle is a contest sort of site, and people take it very seriously, and it's an open contest still, and there are some people that receive literally 100% accuracy on their submissions. So they obviously are not overly eager to give you the answers to that question. So that kind of is an interesting challenge. I've actually been looking at that. I personally don't like it because without the answers, how do you do your confusion matrix, right? But anyway, so write a Python program that will produce the desired results and prepare a presentation for your team that exhibits your findings. Perform the following steps. Load everything, all your libraries as always. Read it with pandas, and then use sklearn to do some processing. Explore the data set by paying attention to the following: which features are available in the data set, what features are categorical, numeric, and what are mixed. What visualization methods, use some visualization methods to do some analysis, and perform the data pre-processing by doing the following. You want to do some cleansing, some reduction, and converting categorical values to numeric. Reduction is going to mean get rid of the attributes that don't really matter, so the features that don't seem all that important. Model and make a prediction of using supervised learning, using the 4 listed approaches: K nearest neighbors, decision trees, bagging, and boosting. Again, this is probably a great idea to use a sklearn pipeline. And then use the appropriate tools to compare the models in terms of accuracy, speed, robustness, and scalability. So it enumerates the kind of the dimensions to consider. Read the .tab file provided below for orange processing. Again, do the CN2 model. So basically create some rules, perform metrics on the classifier, and compare those with what you get up here. And for an unsupervised model, build the clustering model using k-means by varying the relevant parameters, measure performance in terms of those listed. And so that's kind of a common theme that you're hearing. What do you turn in? So a PowerPoint presentation that contains an overview of the work you did, talk briefly about the algorithms that you used, results of your data exploration, provide detailed analysis of performance metrics, so how well did they do on each one of those. Lots of like pretty graphs or grids most likely, and tables. Your data can be split into 2 sets, or it has been split. The train is labeled. It does have the survival flag. Test does not. The training set should be used to build your machine learning models. For the training set, we provide the outcome, also known as the ground truth, for each passenger. Your model will be based on features like passengers, gender, and class. So those are certainly, it tells you the 3, which incidentally are also the ones that are in that orange file. You can also use feature engineering to create new features. So you can do things like create buckets of age groups, perhaps, or family size, because you could figure up the number of siblings and parents and yourself to figure out what the group size is like. That might or might not be useful. Maybe even groups or buckets of fares and so on. To test, the test should be used to see how well your model performs on unseen data. For the test set, we do not provide the ground truth for each passenger. It is your job to predict the outcome, but you can't really validate it. So I'm actually not sure I like that, and I'm working through if I want to fix it or not. But anyway, do what it says for now. I may give you a bonus file, so to speak, so that you can see how well you did. For each passenger in the test set, use the model you trained to predict whether or not they survived the sinking of the Titanic. So given this, you're not going to necessarily be able to produce a confusion matrix. Here's an overview of the data. This is, as you can tell, the train set, because we do have a survived flag. The test set looks just like this, except that's not there. And if you're interested in going and downloading the Kaggle competition information, all that good stuff, there's your link. If you Google Titanic and dataset, you're probably going to find the Kaggle link anyway. And with that, I've reached the end of what I have to say. As always, if you have any questions, let me know. That's what I'm here for. Stay safe, and I'll speak with you soon.